to welcome Richard Alley to give our OCRN Distinguished Lecture. We've been wanting to get Richard over here for quite a while, but he's in such tremendous demand and has such a speaking schedule that finding a window has always been difficult. So it's ironic that just partly because of this funny electronic world that we're now living our lives in these days, it is finally possible to hear Richard's words of wisdom. I can't exactly remember the first time I met Richard, but at least the early times were when Richard was chairing a U.S. National Academy report on abrupt climate change, and I was working on that too. And at about the same time, Wally Broker had put together a group called Changelings, which was looking at glacial geology and abrupt change. And we spent a lot of wonderful time walking around on moraines in New Zealand and in Switzerland and all sorts of fun places like that. And that's where I actually, learned what a moraine looks like and what all of this stuff actually means. You just can't learn it from looking at papers. And I learned a lot from Richard and from George Denton and all the others that were in that circle. So over the years, Richard has contributed fundamentally to both glacial geology and glacier modeling and ice sheet modeling and ice shelf modeling as well. And you'll get to hear about some of these very important scientific issues or underpinnings of a lot of the global change problem. But of course, Richard is an outstanding scientific communicator. He's a TV star. Spent a big chunk of his life, of 1 year of his life, on a PBS series on the environment, on climate especially. And he's the author of an absolutely marvelous book called The 2 Mile Time Machine, which I very strongly recommend everybody to read. And you can tell us scary things about the Thwaites Glacier today. So, of course, I'm not going to even start mentioning all of Richard's accolades because we'd be here until the middle of next week if we did that. So let's go right on to the scary stuff about the Thwaites Glacier. Richard, take it.
Oh, thank you, Ray. Among many other talents of Ray's, and I've learned science from him and so many other things, but I truly remember him instructing me on what kind of wine one should be drinking during a field trip to New Zealand. So thank you so much, Ray. At any rate, it is an honor and a privilege. You are doing fantastic things at Oxford. Of course, you're Oxford, so this is truly wonderful. And let me try that again. Pointer options, get the pen, and there we go. So I'm going to talk to you about tipping Thwaites Glacier. Thanks to Alan and Tristram for setting this up. Thanks to Ray. I've learned so much, and thanks to all of you for signing in. Okay, so I am like a bunch of you, like a whole bunch of people. I did help the IPCC. I got called in first for the second assessment because there was a fight about whether West Antarctica would collapse or not. We're still having this discussion. So our level of understanding has gone through the roof, but we still don't know. And so you may recognize some people in the fourth assessment here. In some very real sense, the IPCC is the mother of all committees. If you were to print out all the pages of all the official IPCC reports and stack them up, they would not fit in this room. So, but the big picture, if you actually do this, is, the news on climate is usually not great. I'm not making anything up there. But what the IPCC really says, if you were to take that pile of papers and turn it into a tweet or two, what the IPCC really says is this. Imagine a future in which we pretend that climate scientists are evil liars. And that's not as far-fetched as it might seem in certain countries at certain times, but versus a future where we make efficient use of our knowledge. And the IPCC is very clear. If we make efficient use of our knowledge, we get a bigger economy. Bill Nordhaus was on this committee. He won the Nobel Prize in Economics in 2018, co-recipient for the work that shows that dealing with climate and energy helps the economy. We get more jobs, we improve our health, we improve our national security. And by the way, the environment is cleaner and we're more ethical. Right now, and I could give this talk someday. This one is the one that has the American Petroleum polka in it. But right now, it doesn't matter if you're a hard-nosed business person or whether you're a tree hugger. The future is in the same direction. And let's be honest, today's students are the first generation in all of human history that knows that they can build a sustainable energy system. And that's a huge statement, and it's a really important one. Now, if we don't, right, the sea is going to rise, and it's maybe going to rise a lot. And that's where I'm going to take you today. I'm going to put some frame on uncertainties in the world. We'll go here first, right? So this is a triumph of observation. This is the satellite altimetry of the ocean. This is truly an amazing thing. Starts in '93, and the ocean is rising. Absolute fact. I was advising certain persons in government, and they would call up right about here and say, why are you lying about sea level rise? This is El Niños and La Niñas moving water onto the land and back off. Once you fill up the lakes, they drain. You can't save ourselves from this. But they'd say, why are you lying? And then they'd shut up. And then they'd call back and say, why are you lying? And then they'd shut up. This is all true. But yes, sea level is rising. That does matter. And I'm going to be a little US centric here, although we're probably not the center of damages. But this is a picture I swiped from the web using under fair use. This is not a storm, it's a high tide. This is not a canal, it's a street. This is what they call adaptation. You don't want waves in your front yard putting salt water on your plants and killing them, so you put up a no wake zone sign in the middle of the street. This is a parking garage in Miami. Again, this is not a storm, it's a high tide. This was not thrown in here by hockey fans, it swam in. This is what they call nuisance flooding. But at some point, the nuisance becomes expensive. And for Miami, it'll be money. For much of the world, it's people losing their houses, their lives. They have to migrate. They become climate refugees. It's pretty clear that the costs and the damages of rising ocean are super linear. A little bit of rise is a nuisance, more rise, and you have to pay for it. And so a little more rise can mean a lot more cost. And bear that in mind when we go to where we're going. This is a picture from New Orleans. This is a hurricane that did not get over the levee. It stayed out. I would not have wanted to be the police officer there, but unless we get started really fast, enough rise to go over this wall is pretty much baked in. What we're going to talk about is the possibility of rise that would disappear out the top of the picture. And you can raise this wall, but whether you can raise it that far is a real question. So go back to the data, squeeze them down as the IPCC did. So the previous slide is this little thing here. Add on some history and add on some future. By the time our students are old, the single most important factor in sea level rise is the decisions that we are making now. By the time you get out very far, the other uncertainties are not the most important thing. The most important thing is what we decide to do. Right? So that's pretty clear. But what I'm going to talk about is the possibility that under strong warming, we just blow off the top of this chart. Why is this? You all know this stuff, but why is this happening? Sort of, kind of vaguely. It's a third melting of glaciers in the mountain and putting water in the ocean. It's a third the ocean expanding as it warms. It's a third ice sheets, mostly melting on top of Greenland. And then a little noise from groundwater. We are pumping water out of the ground faster than it goes in some places. We are building dams that make reservoirs that raise the groundwater in other places, and those sort of kind of vaguely balance. The detailed balance evolves from year to year. It has evolved over time, shifting towards more ice and less thermal expansion, but sort of kind of all of these matter. If these continue to matter over the next decades. Yay, we're happy, we're lucky, we missed the worst. If the others don't matter, then the ice sheets are collapsing and we're screwed, right? So that's a technical term, but right. So once we've melted all of the mountain glaciers, put all their water into the ocean, it's sort of a third of a meter, maybe a half, maybe a quarter, sort of a third. Ocean thermal expansion, it depends a lot on where the heat is going. Is it going into cold water or hot water? Because they have different coefficients of thermal expansion. But it's, you know, a third, a fourth, a fifth of a meter, maybe half a meter or a little more per degree, but not a lot. The ocean is only a couple degrees warmer than it was at the Ice Age. The ocean mixes slowly. You can't have really large, really fast sea level rise from expanding the ocean. Greenland actually is about 7.4 meters of sea level equivalent. Antarctica is a lot more equivalent. To reasonably good approximation, the question of large sea level rise is a question of the flow of the big ice sheets. The IPCC projections under strong warming, RCP 8.5 by 2100, they say the ice sheets will contribute less than 1% of what they can do. The ice sheets will keep more than 99% of their sea level equivalent in the ice sheets. That is the worst case scenario in the quantified numbers from the IPCC, is less than 1% comes out of the ice sheets. Okay, it's really hard to make a better scenario than that. It's really easy to make a worse scenario than that. Okay. So let me walk you through here. This is Kurt Cuffey. He studied with us as an undergrad. He's a distinguished professor at Berkeley. He's the lead author of the textbook in our field, The Physics of Glaciers. If you were to get The Physics of Glaciers in all its glory and read through it, you would find out that we're dealing with a gravitationally driven viscous flow. We do not have to worry about Coriolis accelerations or compressibility. It's mostly longitudinal deviatoric stresses and a basal drag. But the deformation depends on the second invariant of the stress tensor, so it's full Stokes. The hardness of the ice to deformation is a tensor quantity that evolves with lattice preferred orientation, and it also depends on temperature, which is carried by the flow. The basal motion goes from essentially nothing up to dominant. The flow law goes from linear to plastic. It depends on the hydrologic cycle, which has really fast changes and is linked to the temperature through the melting of the ice. This is what we get to do. This is fun. It is really fantastic. Here's the 101 version, right? So this is my dear wife's arm. She is making a pancake. If you make a pile, whether it's a pancake or anything else, it tends to spread under its own weight because the pressure under the pile is higher than the pressure outside. And if it was water, it would spread faster, you know, but piles tend to spread under their own weight. If you make it stronger, it doesn't spread as fast. If you hold it back, it doesn't spread as fast. If you make what's under it bumpier or less slippery, it doesn't spread as fast. Okay? And it sort of looks cool. Now, this is Cindy making a waffle. This is the same thing in nature. Okay, so over here, we are in Alaska. The Juneau Airport is this little runway right there. The cruise ships come up here in the days when there were cruises before COVID. And up here in the mountains, snow has piled up faster than it melted. It made a pile. The pile spreads under its own weight. So just as the waffle is spreading, the pile is spreading. It goes down the grooves in the waffle iron and it makes glaciers that people go to on their tours. It's just the same thing. So if you can think of this waffle, think of the Juneau ice fields, it's the same thing. Okay? If you go up on the Juneau ice fields, up in here someplace, this is what you'll see. So here's some Penn Staters teaching at the Juneau Ice Fields Project. So that's what it really looks like. But it's just a pile of snow spreading under its own weight, squeezed ice. Greenland, Antarctica, really big piles, but otherwise the same story. Pile up in the middle, spread under its own weight, melt or break off bergs at the sides. Okay. This is a vertical thin section from an ice core from West Antarctica. This is about 10 centimeters on a side. We're in cross polars. There is a very strong lattice preferred orientation in here. There is a grain size. There are orientations of grain boundaries that may allow slip. This is something to do with how the ice deforms. This evolves over time, but it doesn't evolve very fast. It doesn't change very fast. We do research on this. We love doing research on this. I'm not going to say anything more because it's not really important. So the strength of the ice and the cooking the pancake to make it stronger probably doesn't change enough to worry about in the near future. If I got my spray olive oil and I sprayed it on the waffle iron, it would spread faster. If I didn't have so many bumps, it would spread faster. Okay, you can change the lubrication, and in particular, you could spray on there and lubricate it. That does change. It's something we need to worry about going forward. But no, Greenland is not going to fall in the ocean. And the reason Greenland won't fall in the ocean is it really is on a waffle iron, not a greased griddle. Okay. So this is the edge of Greenland on the west side. This is a summertime picture. The edge is pretty flat. It's flowing over the waffle iron, and that flow with the longitudinal stresses makes low spots in the surface. When it melts, the water flows into those low spots and makes these lakes, and they are kilometers across. They are meters to tens of meters deep in the middle. You can sort of tell they've been growing. There was a stream, here's a stream, and the stream flowed on into the low spot, but now the stream is underwater as the water has grown. But there's also crevasses here, cracks. Right, and we actually, I'm vaguely proud of this. We wrote a paper in 2005 and said, this is just like volcanoes upside down, and this is the magma chamber, and it's going to drive a dike, and it's going to break, and it'll go fast if it goes. And that was sort of a prediction. Thank heavens, our former student, Sarah Doss, was not in the lake in her boat when it drained. They had been working on these lakes in boats. And here's Sarah in the middle of the lake, except the lake is gone. It broke through, it drained to the bottom. It was doing twice Niagara Falls for an hour. There were earthquakes. The ice is lurched up as the water gets to the bottom and it shoots out the front. There were blocks going. There's a big block down there that fell off of things. This was really, really, really dramatic. And no, the ice sheet did not fall in the ocean because it's on a waffle iron, not a greased griddle. And the truth is, by taking the lubricant and concentrating it in time and space, this may actually reduce the total motion of the glacier. Because the waffle iron is there, it happens. So this matters. I would love to talk more about this because it's so much fun, but it's not the big thing going forward for near future sea level rise. Okay. Now we'll go to the one that is. So here's Cindy holding back the spreading of the pile. Do glaciers have things that hold them back? And the answer is yes. So an analogy, we might go to the spatula. I'm also going to use this for the analogy. It's more fun. All piles tend to spread under their own weight. The early Gothic cathedral builders discovered this. They had a tendency for the walls to bulge out and the roofs to cave in. And so they invented the flying buttress to push back on the wall to keep the pile from spreading. And as it turns out, ice sheets in cold places have flying buttresses. They have spatulas that hold them back. So here's an ice sheet. It's a big pile. It's spreading under its own weight. It gets down to the ocean. If it is cold in the air and the water, where the flow is fast, it flows over the ocean, it runs aground on a place like this and generates friction. And usually, more importantly, it's in a fjord, there's friction on the sides. So you have drag on the sides at a place like this in the third dimension. That drag holds back the non-floating ice in the same way that the flying buttress holds back the spreading of the pile of the Gothic cathedral. It's minus 50 up here. It's not going to melt. It is close to melting here. Every ice shelf on Earth is melting there. They're all at the melting point. And so if you wanted to hurt a Gothic cathedral, going after the flying buttress is a terrible thing to do because it would work. If you want to hurt an ice shelf, you warm the ocean, you warm the air, you take off the flying buttress, the pile spreads faster, and it raises sea level. Whoop, that's not what we wanted. So here is a map of Antarctica. The flying buttresses, the spatulas, the ice shelves are in color. The color scale is how much is pushing back. And the darkest blue way over here is not pushing back. It's freely spreading. What you'll notice is there's virtually nothing on this plot that is in the darkest blue. There's a bunch of sort of lighter blues in here, which are only pushing back a little. And then there's a whole bunch of the yellow to brown, which is pushing back a whole lot. So there's a number of things in this. One is, yes, the ice shelves are keeping the pile big and the ocean little. Two, when the ice shelf flows past its last pinning point, the last island or the last edge of the fjord, it breaks off. The ice shelf actually needs the support of that friction, that buttressing to exist. And once it gets to open ocean, it doesn't spread long distances over the ocean, open ocean, it breaks off. I'm going to take you up here. You may have seen this before, but we're going to go up to that little corner up there. It's a fascinating thing. Chris Stokes with the British Antarctic Survey back in '98 said, if this were on the previous plot, this would be blue over here, and this would be yellow in here. And this is one of these flying buttresses. This is the Larsen B ice shelf. And Chris Stokes said the big iceberg can break off the front and it won't matter because that's blue. But if it breaks back into the yellow, it'll keep breaking. This is a prediction that when it breaks back into the yellow, it will keep breaking. So that's predicted in '98. 4 years later, this is 2002. This is the same thing that was in that model of Chris Stokes, except rotated just a tiny bit. Ocean is in black down here, the Antarctic Peninsula over here, mountain range with glaciers dripping off of it. The floating extension is in the middle, the flying buttress, the ice shelf. You can see the scale bar over there in the corner, 20K. And the funny colors like this are lakes on top of the ice shelf. This area had warmed, and it made lakes like the one that Sarah had up on Greenland. But now it is not on a waffle iron, it's on a greased griddle. It's floating, there's ocean water under there. And so Chris Stokes said, when you first break it here, it'll just keep breaking. So this picture is January 31st, 2002. 5 weeks later, it's this. So retreated at about 10 kilometers a week. This is brittle control. The blue slushy back here, you could kayak through this. This is just broken up stuff. As the icebergs fall over, they release a lot of energy, they break things. This did not directly raise sea level, but it lost the friction on the sides. The tributaries sped up as much as 7 to 8-fold. That does raise sea level, but not much because there isn't much ice up here. If there were, it would be a big deal. Okay, so you can kill the ice shelf by making it warm above. Now, we don't go to Alaska to study ice shelves. We don't go to South Greenland. We don't go to the northern Antarctic Peninsula. They're all gone. Right? You find ice shelves in cold water under cold air. And I just showed you how you can lose an ice shelf as the air warms. You can also lose them as the ocean warms. If you have not run into Heinrich events, don't worry, but during the last ice age, occasionally the ice sheet in Canada belched out these immense surges of ice. They very clearly were loss of ice shelf, and one in particular happened when the air was the coldest it got during the entire ice age. It was done by warming of the water, not the air. And so you really can kill an ice shelf by warming water as well as by warming air. Once you lose them, there's hysteresis. They must have grown, they're there, but we have seen many lost. We have not seen persistent regrowth of any of them. It's very, they keep trying. There are fluctuations in climate, but they haven't made one come back. So loss is a big deal. This is something I helped a tiny bit with. Ian Jacken did this. We are on the west coast of Greenland at Jakobshavn. We're looking down. This is rock up here at the corner. This is a melange. This is a sea ice mess out here over ocean. And this is an ice shelf right here. This is a flying buttress on the Jakobshavn Glacier. At this time, 2000, Jakobshavn was probably the world's fastest glacier. Warm water gets under it. It thins the ice shelf. That lets the land ice go faster because there's less friction. That generates more stress on the sides. And then the sides started breaking. So you see these cracks in here. And then the entire ice shelf broke off. And then what had been the fastest glacier on the planet doubled or tripled its speed. Okay. So this is a case where warmer, and this is what happened to the Heinrich events, warmer water takes out part of the ice shelf, then the rest of the ice shelf goes. Once it breaks on the sides, it's not buttressed, and buttressed ice breaks off. I brag about this one. This is from Karen Alley, our daughter, who's a new professor at the University of Manitoba. It builds on work from Mark Fonestock and Ian Jacken, and then from Kaya Riverman with us and Knut Christiansen. Ice streams go fast. They have little troughs in the surface along their edges. When those troughs get to the ocean, they float up and they make highs in the bottom. When the warm ocean water attacks them, it makes plumes that go up the sides of the ice shelf. They slice up into the ice shelf and it's ready to break off. And so this wonderful paper of hers, and I got to help a tiny bit, all the ice shelves are preconditioned to break. This is not good news. Okay. And the Antarctic is losing mass. This is freshening the surface ocean a little bit. You may have seen the paper or two that said, oh, it's okay. We won't have meltwater on top because the Antarctic will get cold because all the melt will come out and they'll put a cap over the top of the Southern Ocean. And so we won't have really strong warming quickly in the Antarctic, which may be true. But now what happens to that warm water off the edge of the shelf? It mixes up the isopycnals and it outcrops out in the Southern Ocean. What happens if you freshen the surface? The isopycnals wrap over and you just hose hot water right at the grounding zone. That's what happened to the Heinrich events rather clearly. You can't save the Antarctic by putting a freshwater cap out here. It may be worse. And so there's a real picture. If we make the air hot, you're going to take out the shelf. If we make the air cold by freshening the surface ocean, you're going to take out the shelf. Okay, you're darned if you do and darned if you don't. So it's pretty clear that in a warming world, we really do risk loss of shelves. This is a cartoon from a review we did a few years ago. In places with cold air and cold ocean, you tend to have an ice shelf that buttresses. And then as I'm going to show you, the ice almost always ends at a bottleneck, a place where the bed is high or the fjord is narrow or both. If you lose the shelf, you usually kick it off the bottleneck and it retreats to the next bottleneck. And that's what we're worried about. So let me show you a bottleneck retreat that has nothing to do with Antarctica. This is Alaska. This is Glacier Bay. In the old days, before COVID, you could get in a cruise ship and you could go way up here and watch little tiny weeny glaciers making little tiny weeny icebergs. And it's just gloriously beautiful. This is Icy Strait at the bottom. That's Glacier Bay. Glacier Bay is about 100K long. Okay. When Vancouver went by in 1794, Glacier Bay did not exist. It was full of ice. When John Muir went by in 1888, it was mostly open. I'm going to show you looking down from space. So this is it. Icy Strait at the bottom, Glacier Bay up here. The ice had advanced out here to this bottleneck. Big area, lots of ice trying to get out of this little narrow thing, which is also shallow. When it retreated, then it ran away. It was headed to the next bottleneck and it went all the way up to where it is now. So it went that way. John Muir saw it. It was up here and way up here when John Muir saw it. I'm going to show you this little corner, just this little tiny bit of this place viewed there. Okay. If you went there in 1941, the icebergs were breaking off right down in the corner, and this is the glacier. You went by 9 years later from the same rock. It's there, and there's where the icebergs break off. And now, you know, it's back around the corner. And it's sort of gross to watch, but yeah, okay. So at any rate, what happened to the ice thickness? You can now take your boat up to here. Red is it thinned by 1,500 meters. It did not thin by 1,500 meters by flowing out the bottleneck. It thinned by backing out of the bottleneck, breaking off icebergs and clearing. So this is a place, you kick it out of the bottleneck, it retreats to the next bottleneck. You thin hugely, it goes really fast. Okay. This has been observed for the Laurentide ice sheet, for the Fennoscandian ice sheet, for Svalbard, for Chile, for Alaska, you know, wherever we look, marine ending ice stabilizes in the bottleneck, where it's shallow, where it's narrow. When you kick it out, it goes to the next bottleneck. Normally, it's a narrow fjord, or it's not very far to the next bottleneck. The event is locally spectacular. It is globally insignificant. If you do the same thing in the basins of Antarctica, West Antarctica is 3 meters of global sea level. Thwaites, the Wilkes and Aurora are more. So if you do exactly what has happened in a whole bunch of other places in Antarctica, the bigger basins matter to the world. So here's Antarctica, and red is thinning. And we're going to go over here to the corner to Thwaites Glacier. This is the bed of Thwaites Glacier. Dark blue is 2,500 meters below sea level. Now the ice is not floating. It's 1,500 meters above flotation. It's 4,000, almost 4,000 meters thick in places. But this is the bed of West Antarctica. It's there because of rifting. It's the West Antarctic Rift System. The ice wants to flow along the rift because that's the easy way to do it. But it's a very long way to the ends. And so it's built up in the middle, and then it leaks out the sides. And we're especially worried as that's the first place that's likely to collapse, is that leak out the side. That's called Thwaites Glacier. Here is a different version of Thwaites Glacier showing the bottleneck, and then on the left is a possible analogy. The analogy isn't bad enough because it needs another couple of decks funneling cars vertically as well as horizontally. So you go from very deep to very shallow, you go from very wide to very narrow when the ice is trying to get out the bottleneck. This is a little bit of modeling from Dave Pollard, Rob DeCanto. I helped a tiny bit. Present, you're trying to get ice out a fairly narrow outlet. And these light colors say that it's not very deep either. So it's narrow, it's shallow. If you just retreat, the dark colors say it's thicker and the length is much longer. So you can get rid of way more ice. All it has to do is retreat. Now, we've also seen that when it retreats, it will go faster. So it won't just be wider and deeper, it'll also be faster. You get a lot of sea level rise that way. You don't need any new physics. It's just what we've always seen acting in this big place. So that leads us to the question, will we retreat from the bottleneck? And this is what a lot of us are working on now. The answer is probably, but not certainly. Okay, we may miss this. So this is a simple model that Byron Parizak did a few years ago. Others have done it since. They get the same basic answer. This is air up here. This is ice down here. This is rock down here. And this is ocean over here. And what he's going to do is kick this, sort of like getting rid of the ice shelf. And he's going to ask whether it retreats. And what he's done is he's put it on a viscous bed on the left and a plastic bed on the right. And what you're going to see is that the viscous bed is going to collapse and the plastic bed is not. All right, boom. Now, what was going on? The viscous bed localizes thinning near the coast. That lets it float off of the sill. That moves the grounding into the deep water, and then it goes to heck. But if he makes both of them actually collapse, the plastic one then goes way faster. So the viscous one retreats early, but it retreats slowly. The plastic one retreats late and it retreats fast. The real bed is probably both. It's spatially viscous plastic, viscous plastic. Most models are not able to do this. They can vary the lubrication, but they're not very numerically stable if you vary both of them fast. We had a student, Stephen Kollner, working with Byron and me and some others, who did some idealized modeling and made the model stable enough you could do it. Usually if the bed is mixed, it falls between the end members, but sometimes it's more extreme than either one. This is something that actually will have to be done right. And so far the models are not really ready to do it right. It's frustrating. Let me go back to the bed. So this is West Antarctic's bed. And now let's zoom in, and it's the same color scale underneath there. And flow is on top, showing it comes into the bottleneck. And Sridhar and company went down and they did geophysics. And among the geophysics they did is this fantastic new swath radar. And they can now do swath radar. So this is a 10K bar. The darker blue is deep. The lighter tan is shallow. The relief here is 700 meters. These flutes are hiding behind fault-raised blocks. They're 100 meters high. They're 15 kilometers long. They often end in these giant troughs eroded around the upstream end of bumps. And if we back off and lay some seismics on, they have seismics on this, it's rock, and then it's mud, and then it's rock, and then it's mud, and then it's rock, and the mud is pretty clearly plastic, or nearly so, and the rock is pretty clearly an interaction that gives rise to something that's more nearly viscous. And then you've got all these funny things that are going to channel the lubricating water, and nobody has come close to putting anything like this in a model to find out whether it really will retreat or not. So then there's sort of one more point that we have to deal with, and then we'll frame it and get out, okay? So this is a picture of Helheim Glacier on the southeast side of Greenland. The cliff right here is the height of Big Ben. It's a little higher than Big Ben, so that's 100 meters. This is a place that has these giant iceberg calving events that make magnitude 5 earthquakes. You can see them on YouTube. They're really, really exciting to watch on YouTube. But it's a fascinating thing that even though it makes these breaks that make magnitude 5 earthquakes, it still is rate limited by viscous processes. It breaks to just above flotation, it thins to flotation, and then it breaks again. This kind of process acting in West Antarctica could blow the top off the IPCC numbers. It could greatly increase sea level rise with this viscous limitation. It has to thin by viscous processes to near flotation, and then it breaks a little bit above. There's a real worry if you retreat in Antarctica that rather than having one Big Ben high subaerial cliff and 10 Big Ben highs in total, you know, this is a kilometer high cliff and 900 meters underwater, that you'll get something 2 or 3 times that. And there's, for a long time, back to Hansen and Hook in 2003, we have had a pretty good idea that the cliffs can't be too much higher than this, or it will switch to brittle limitation rather than viscous. And if it's breaking from the high stress rather than having to wait to thin, it could go really fast. And we don't even know what the worst case is. I can tell you nobody has published a worst case yet. The people often point to this work by Dave Pollard and Rob DeCanto as a worst case, not even close. Okay. So, I mean, if you want a horrible thought, it was floating ice, not grounded, but Larsen B retreated at 10 kilometers a week. So yeah. I'll guarantee you that we don't know that this will happen. Maybe it won't. There's a lot of ways I can think of that we might dodge the bullet. But this is certainly plausible based on observed physics. There's nothing new that's needed here. And it's important to remember the orbital forcing that caused high sea levels of the past arrived over 10,000 years. It didn't arrive over 100 years. An RCP 8.5 type forcing is going to be bigger in size, speed, and the amount of ice it affects than anything since we ended the snowball Earths. Right? We can't calibrate this properly on paleoclimate because paleoclimate didn't do this. So there's huge uncertainties, and there's a real concern here, right? I took the broken things class when I was a student, and and the broken things professor said, look, calculate it to 5 significant figures and then make it 3 times stronger because you'll never get it right to a factor of 2. This is one of those cliffs. It's ready to break. Okay? We're trying to get this right to a lot better than a factor of 2, and a good engineer would say, don't you dare get yourself stuck where you have to do that. So I want to close with a framing here, right? So now I teach from home. I used to ride my bicycle to work. I want you to think of commuters in a place where they have traffic, going into London or going into DC or something. So I wanted you to think of a commuter in a place with traffic and think about the problems that a commuter faces and how likely it is that they will face those problems, right? Normally what happens, you get stuck in traffic, you turn on the radio, it's boring. Best thing in the life of a commuter, there's no traffic and it's really fun radio. That won't happen to you. You're going to sit there for an hour and they're testing the emergency broadcast system, right? But why are you sitting there for an hour? Because somebody was run over by a drunk driver and then they're clinging to life at this point. And so what we expect is way on the good end of what's possible. And what do we do about that? We have cars with seatbelts and crumple zones and airbags, and we support traffic engineers and we support police persons to try to keep the drunk drivers out. We put a lot of our money into something we don't expect because it's so bad if it happened. Now, if you take what the UN says and you run it into economic models, we are hurting ourselves economically because we're not dealing with climate change. And then somebody says, but you're not certain. Yeah, we're not certain. It could be a little better. It could be a lot worse. And I've done this. I've gone down to the US Congress, to the Senate and the House, and I've testified, and I've had this discussion. And I say, this is what we know. And somebody says, couldn't it be better? And I say, this is what we know. And they say, couldn't it be better? And then they say, see, we heard both sides. Well, come on. Right? This is very interesting. Now, you'll see Ray Pierre Humbert right there, right? The U.S. National Academy, the Royal Society have looked at this. There are ways we can deal with uncertainties like this. We can anticipate surprises. We can design for risks. We can take out insurance. It is indeed possible. But just leave it with the discussion question, and then I'll shut up. You're the captain of the ship. You know there might be icebergs ahead. It's fog. Do you turn off the radar, turn off the sonar, and tell the watch to come downstairs and then speed up and blast forward? Or do you do a little research, turn on the radar, turn on the sonar, get the watch up and slow down a little bit to see what's coming? At any rate, I will shut up there and see if there are any questions in the chat. Thank you so much for inviting me. It's an honor and a privilege.